Okay, we'll get started. I'm delighted to welcome Dr. Naman Shah. I think you had presentations from a broad variety of people. We had some researchers earlier on. But I'm deliberately also, selecting those people, people coming from different kinds of jobs, in different kinds of. So when you hear from them, you get a sense. All of you will go into different directions and look for different kinds of jobs. It'll be good to get an idea of what people have done when they are in that particular type of job. So you heard from somebody from Google, you heard somebody from Apple, and number of these companies. You heard from some academics and professors. You'll hear from two professors from our department later on. So Naman got his PhD from Arizona State University. He was a postdoc at Brown University, and now he has joined A2I. So A2I is an exceptional place for doing research. It's a sort of a research lab funded by Paul Allen. Am I right?
Yes, your voice is.
He also the other he is working on an area. One term being, my voice is not coming right.
Sorry.
My voice is okay, right?
Now it's okay. In the, at some point it started to break, but now it's okay. It seems to be fine.
Oh, yeah. I had my view. I was looking at the class, and perhaps that's why the direction was wrong. So um, so as I was saying that there'll be explosive growth in something called embodied AI and physical AI, and that does involve robotics and AI, and Naman works in that area. So he works in an area of that will have likely great growth. Plus, he wants to plus his journey is very interesting. Of course, his heavy research heavy journey. So with that, Naman, please go on.
Yes, thank you, Professor Shade, for inviting me. It's a great pleasure to be talking at the AI Institute at the University of South Carolina, and thank you everyone for being there. So, just as Professor Shade mentioned, I did my PhD at Arizona State University, and then I did a postdoc for about 1.5 years at Brown University, and I very recently, just a couple of months back, I joined. Allen Institute for Artificial Intelligence as a research scientist. So the work that I'm going to be presenting today is mostly from my PhD at ASU and my postdoc at Brown. I have just started working at AI2, so not a lot of work has been there yet, but hopefully very soon we'll have a lot of work as well. So, and as Professor Shade mentioned, you are hearing from various places. I know someone from Google and Meta talked in past couple of weeks. This presentation is going to be slightly different from them because this is going to be very research heavy and not a lot of engineering there. So yeah, so let's talk about what I have been working on learning world model representations for robot planning. Okay, so with that, we want robots in our life. We want robots to do different things for us, and especially things that are mundane or that are very boring for us. For example, I don't really like cleaning my apartment so much or doing dishes. So I want a robot to do that for me. And we want the robot to be able to do that automatically. I don't want to have to show it like 100 times or 1,000 times how to do it. So what we want from the robot is can be very succinctly mentioned as a goal-directed policy synthesis. So I asked the robot to accomplish a task, and then the robot should come up with the steps that it needs to perform in order to achieve that task. So let's say if I ask robot to go and get me coffee from the kitchen, it should automatically come up with actions such as, okay, I need to go to the kitchen, I need to find the coffee mug, put it in the coffee machine, turn on the coffee machine, and bring the coffee mug back to Naman, wherever I'm sitting. Right. And by the way, feel free to interrupt me at any point. If you have questions, please feel free to ask. Right. And the robot should be able to do that on their own. And where are we right now on that journey on achieving that? So these are some demonstrations from a company called Physical Intelligence, and then the Google DeepMind. These are from previous year or last year actually, and they might have updated their demonstrations. But in general, we are seeing a lot of growth in robotics and these capabilities. However, there is a catch there. So the catch is, first of all, they are very short horizon. So they are not general purpose robots that can do different things for you. Each robot comes with a particular skill. And now if someone tells me that I need to buy a separate $70,000 robot to do my laundry and separate $70,000 to do my dishes, I am not going to be able to afford that at all. And no one would be able to afford that. So we want a single robot that can do a lot of things and without showing. So in this case, these people are using something called behavior cloning or imitation learning. And the limitation is, first of all, each task that you want the robot to do requires so many demonstrations from an expert. So in this case, more than 5,000 demonstrations for each task. And after even that, it can only do roughly 75% task that they have been shown to do. They do not go beyond these tasks, exactly the tasks that have been given. But on the other side, when we compare our robots with humans, when we look at humans, let's say you're coming to Seattle and you reach out to me and let's can we go for a lunch? And I say yes, let's meet at Jai Thai. For a human, it's very easy to just look up the Google map, identify where Jai Thai is, find a route to Jai Thai, and just meet me there. We have never accounted for this situation ever. We have never met. We have never came up with a plan to go to this particular restaurant from the location where you are in. But we can still do it, and we can do it very easily. Why? Because we have this model of the world with us. In this case, a map and a model that we can use to plan. That you don't need to think. Okay, I can walk. You know, you can walk or take a Uber or take a drive a car there. Right. So that is because we have something called world models in our head. I like to. There are many definitions of world models, and people disagree on what a world model is, or people agree on world model is. But I like to broadly categorize world models in implicit and explicit. So implicit world models are something that are very low level. They are more like pixel based. If I ask, okay, this is the image, and if I take the action, what the next image would be. Or there are explicit symbolic world models, which says, okay, the robot has an action that is basically pick up something. What happens at the high level when robot executes that action? And there are different works. So my work basically falls on the explicit world model parts where we are learning these actions at the high level so we can do long horizon planning. But there are also a lot of work in learning low level pixel based or transform based diffusion based world models by Danny Hefner. You would have seen the very famous paper called Dreamer, which was recently accepted into Nature. So to me, a world model is a model that predicts an outcome of an action in a state. And that is the key assumption. Or that is not just assumption, but that is the key capability that even humans have in order to be intelligent. We are intelligent because we know what is going to happen when we take actions. And compared to children, when they are growing up, they don't know if something is hot and I touch, I'll burn my hand. But we know that, and that's why I mean we adults usually less are less prone to those things. Mathematically speaking, there have been a lot of focus on modeling the world or predicting things. This is a famous quote from Laplace back in 1814, where they say that if we can measure each location and the speed of each and every particle in the world, we can predict the future. Here here the emphasis is that predicting the future is a very key capability in order to be better, right? But going back to the example that I had, humans have world models, but they are also at the very different level. So let's say we decide to meet at me meet to this place on Sunday afternoon. Given this is Friday, you won't think exactly how you are going to reach to this place today itself. You will say, okay, let me just check if I can take an Uber right now. Maybe yes, fine, and I'll reach there. uh, in the morning you will realize, okay, I'll be ordering an Uber, let's say at 11:30. I'll sit in the Uber will leave me there at around 11:45, and I'll meet Naman. Then when it actually comes to ordering the Uber, you will think, okay, I'm going to go down to the apartment, open my phone, open the Uber app, and book an Uber. So we make decisions at different levels of steps. We don't make and let's say while then the last step is while walking, you don't really think, okay, where my joints are going to be, or how my leg is, I'm going to put my leg. Those things come implicit to us, right? So similarly, robots also have different levels of planning, or robots also need to do different levels of planning. The lowest level of planning that the robot must do is at the control level. That is basically deciding how much torque or force goes into each joint of the robot or each motor of the robot. And usually we use something like a PID controller, or an impedance controller, or a compliance controller at this level. Now, that level of planning already requires you to know where the robot's joints are going to be, right? And that is the job for low level planning, or what I like to call low level planning, and that is motion planning. So you have different algorithms like RRT, PRMs, and everything at that particular level. And at the end, then there is a very high level planning, which is more like human interpretable high level action. So for example, pick a can. So let's say if robot wants to pick a can, the high level planner will ask it to pick a can, and then from that the motion planner will generate a motion plan that picks up a can, and then the PID controller will follow that motion plan and generate a trajectory that actually does the thing done, right? And for most of the talk, what I'll be doing is I'll be talking about can you see my pointer?
Yes.
Yeah.
Okay, perfect. So I'll be talking about the low level planning and the high level planning, and I would be assuming that the control level planning or the PID controllers are there. And we have seen all these robot dancing, doing push-ups and everything. So there are good PID controllers already there out there, and we should just be using it off the shelf and not in reinventing the wheel. Okay, so first let's talk about the low level planning. Low level planning happens in the configuration space. Now, the configuration space of a robot is basically the set of all joint states, and joint state is assignment value to a joint. So in this case, in this particular two
There's a
particular
question.
arm.
There's a question.
Yes, sir. Are you looking to run control on the robot, or are you trying to have it like IoT connected to like an LLM?
Sorry, can you repeat the question, please? It was not very audible.
Yes, sir. I'm wondering if you're looking for the control on the robot locally, or to be IoT connected, like network connected to like an LLM.
Oh, no, very good question. So the controls are usually very high frequency, roughly 100 hertz or something. So it's very hard to have them IoT connected because of the bandwidth limitations and everything. So typically, control is something which is very local on the robot itself. You can't have controls IoT connected, but you can have high level planning and also maybe low level motion planning also connected to, like, let's say IoT connected. It can happen in the server, but the controls has to be on the robot, and it has to be just local, because again, it's 100 hertz. The fastest LLM I can know to produce the waypoints is roughly 1 hertz, maybe even less than that. But controls has to be at least 100 hertz for a fluent control. So none of the approaches use IoT connected controller. They are usually on board on the hardware itself. Does that answer your question?
Yes, sir. Thank you.
Perfect. So, okay. So going back here, the configuration space here is two-dimensional because it has two joints. compared to this airplane, which has X, Y, Z and roll pitch yaw, so 6 degrees of freedom. And then this bimanual mobile manipulator has 20 degrees of freedom. So the control space or the configuration space is really high. And actions are basically go from one configuration to another. And for that, we do something called motion planning. So how the motion planning happens is you have your configuration space. Some of the configuration space is forbidden because it's in collision with other objects. So what you start doing is you start picking up at random configurations that are collision free, and you keep doing that. So you identify what configurations are collision free and then start connecting these configurations. Now, so, while connecting also the path may go from a configuration, an obstacle which is in collision. So you remove that path and then you build a roadmap like this. Now, once you have a new goal state, you just find a path from the start to goal in this your graph, and that gives you a motion plan. Now a controller will take this motion plan and then execute it on the robot. So this is low-level motion planning. And on the high level, you have your PDDL style planning. There are different algorithms that do PDDL style planning. In that case, you have your domain and a problem. A domain file has predicates and actions in it. The problem file defines what the current state and what the goal is, and then planner takes both of them in and computes a plan for you. So in this case, let's say this is our problem. We have some blocks in some configuration like this, and we want to go from there to the showed goal. Then you will need something like this. Here there are a bunch of predicates that says, okay, what are the relations or properties of the environment. So for example, here is a relation that says block X is on block Y, block X is on table, or there are some properties like whether the hand is empty or not, whether some block is clear or not, things like that. And then you have actions, which has preconditions. So that says what has to be true in the state in order to take that action. And then there is effect, which says that what would happen when this action is applied. So this is basically a symbolic world model. And typically what happens is someone has to write this by hand, and we'll go into depths. So once you have these things, you can do your task planning and your motion planning. So here is coming back to the idea, and coming back to this, that the trajectory planning or control is very short horizon, very small steps. Then you have your motion planning that is slightly longer steps, and then you have your task planning, which is extremely long horizon and long steps. And the thing that combines task planning, the symbolic thing, and the motion planning, the continuous thing that the robot can execute, is something called combined task and motion planning. So what happens in combined task and motion planning is you have a human expert who writes these predicates and actions that I showed in the PDDL file and generates these models, and then uses a symbolic planner to come up with a symbolic plan. Once you have this symbolic plan, you have your samplers, or what we call generators, that says how to refine these symbolic plans into motion plans that the robot can execute. And you use these generators to then go and for each of your high level action, you start computing motion plans. And then you go into this loop of, if the high level plan doesn't work, you need to go and update your problem, and then you will get a new high level plan until you compute this. So this works in deterministic settings. But what if your robot is stochastic? So you don't know whether if you plan to execute some action, it would succeed or not. So in that case, you need a single high-level plan is not necessary, or not sufficient, sorry. And in that case, you will get something like a policy tree. Instead of now having just one chain of actions, now you have like a tree structure, which says, okay, start moving towards your goal. And if you reach the goal, you pick the object. If you don't reach the goal, you still need to keep moving, and you can follow different branches here that gives you some kind of execution instructions. So, but the problem is when you are dealing with these trees, there are so many branches that you need to take care of, and which one would you consider first? So the idea, so what we did was we converted this to a knapsack problem, and we used approximate dynamic programming there and came up with a measure that is basically how likely this branch is to occur versus how hard is to handle that branch. And one, it turns out that if we select branches in that way, that is the most optimal way of doing it. And we have a theoretical proof for it as well. So we tried this approach in different settings. Here is one of the settings, and these are some of my favorite videos as well. So here, one of my friend is placing a plank randomly at one of these two locations, for example here, and then the robot is using this camera to identify where it is placed, and then using it to build these structures with Kiva planks. What robots have been given here are your actions that you can pick a plank, you can place a plank, and how to refine those into low level motion plans. And then robot is coming up with this entire solution that okay, which when to pick up a plank, when to place it, where to place it, and how to place it. And then it is building all these structures on its own. Right. Any questions so far? Okay. However, this is slightly restricting. So here we are seeing what is called motion planning, but there are some problems that cannot be handled using motion planning. Motion planning doesn't let you repeat some actions. Motion planning doesn't let you take into consideration how the visuals change while the motion is being generated or motion is being performed. Also, motion planning doesn't let you interact with a lot of objects because motion planning has to be free space, free of collisions with obstacles. But then there are cases when you want to be in collision. So for example, if you are opening a door, you want to be collision in with the door, so because you want to open the door. Or if you are, let's say, spreading something on the bread, you want to be in collision with the bread, or you want the knife to be in collision with the bread so it can spread the butter, right? And motion planning doesn't allow you all those things. What it allows, but what we can do is we can use reinforcement learning or something called options from the hierarchical reinforcement learning literature in order to do this. Options have three components, basically. Alpha, that is the initiation set, that says, again, that says when an option can be taken. Beta, that's the termination set, and that says that where the robot would be or where the agent would be after this option is taken. And pi is the policy that basically takes you from somewhere in the alpha to somewhere in the beta. So here is an example of an option. So this is basically spreading peanut butter on the bread. And this is very recent work at Brown. So yeah. So here is the robot pouring peanut butter on the bread, and that is the option. You see how it's repeating the process, how it is in collision already with the peanut butter, and none of these things can be done using motion planning. Similarly, here is another example where we are using the Boston Dynamics Spot robot to open these filing cabinet, and you see like how already the robot is in the collision with the thing. Not only that, robot will use its gripper to open it more, which cannot be done using a motion planning algorithm. And let's say you want to use these kind of skills for your task in motion planning. So what we are doing is we are using something called composable interaction primitive here, which connects two skills using motion planning. So instead of going, you can use motion planning to enter the initiation set of the skill, then execute the skill, and then you can go out of the termination set again using the motion planning thing. So here is an example of a chip or a composable interaction primitive. So if you see here, this particular motion is the robot is using motion planning to enter this initiation set, where it can now use the pre-learned skill to open this jar. And then from there, it is using motion planning again to go to a termination set, out of termination set, where it can do other things. So once we have that, we can do task and motion planning over it. And we get some good results with it. That is, you can do some complex tasks, like let's say, for example, spreading peanut butter. Did I take the wrong video? No, yeah, this is correct video. Yeah. So the task is basically to apply some peanut butter on the bread. So you use different chips. This is the chip to open the jar. Then you have a chip to scoop peanut butter on the knife, sorry, and then a chip to spread it on the bread. You can all do all these things, but there is a catch again, as with everything. The task and motion planning, or what we are calling task and skill planning now, requires a lot of inputs from the users themselves. So in this case, you need predicates, you need actions, you need action models, and you need post generators, and those are not easy to write. Even if an expert has to write them, it will take them days to write it, even for simple settings. And these experts doesn't only have to be robotics expert, but also has to be domain expert, because these predicates and these actions depend on a robot as well as the setting where the robots are being deployed in. So the hypothesis is, can we automatically learn these robot and problem specific abstractions from raw data? Or can we automatically learn these models? And so what I've been using, or central theme of my research of learning these abstractions, has been critical regions. The way I define critical regions is a combination of bottlenecks and hubs. So in this example, let's say you are here, you are at this initial configuration and you want to go to this goal configuration. Every plan that goes from these configurations has to pass through this narrow corridor. So that's a bottleneck in the environment that every robot has to do it. But on the other hand, let's say you want to go from here to any of these green dots. And if you go here, this gives you an easy access to all of these green dots. So that is a hub. Another example of a hub would be a side of the table. So let's say if once you go near the side of the table, you can do a lot of things on the table itself. That is also an example of hub. And what we do is we combine them into a single definition to get a definition of criticality measure. So what criticality measure says is how many solutions are passing through this particular region. And now there can be less solutions passing through the region just because the region is small. So we normalize it with the volume of the region and we get this criticality measure. Now what we want to do is we want to learn to predict criticality measures for different environments without actually collecting data in it. So what we do is we do offline training, where we first collect a bunch of data in some training environments. How are we getting this data? We are just solving random motion planning problems in the environment. So here is an example. The robot here is just a rectangular robot that can move in X and Y direction and can rotate along the Z axis. So it has 3 degrees of freedom. And what you are seeing here are some of the critical regions. And you already see that the central area in the bottleneck region is very critical. Not just that, it also shows that when it is in this bottle region, it has to be vertical. And when it in this other region, it has to be horizontal. So you're already getting a lot of information from this. Here is an example with another robot. So right now, instead of just having a rectangular robot, it has a hinge joint that it can articulate. So it's something like a tractor trailer. And you see that here when the robot has to be flat here, and when the hinge joint has to be flat here, and it has to be at an angle to go through this 90-degree turn. Right. So what we do is we collect this data and we then use a unit architecture we train a unit architecture to predict this. So we give it the occupancy matrix of the environment. So basically where the collisions or where the obstacles are in the environment, and then we predict these critical regions. And once this network is trained, you can give it an unseen test environment and you can get criticality for that environment. So that's how we get our critical regions. Now, once you have your critical regions in a new environment, what we do is we grow Voronoi cells around these regions, and those Voronoi cells become our abstract states. Going from one Voronoi cell to another Voronoi cell are abstract actions, and once you have that, you can do hierarchical planning over that. The way I showed previously in task and motion planning, you can do that again, and you get your motion planning algorithm that is using learned abstractions now. Again, if we go into detail, we can prove very nice theoretical properties like downward refinability. What does that mean is, if I come up with a high level plan, it will have an actual low level plan that the robot can execute and reach the goal. and also probabilistically completeness. That is, if there exists a solution, our approach will find that solution. Okay, so we tried this in different settings. So we tried it for navigation problems, that is A through G, and as well as manipulation problems, that are I and J. The training environments that we had were of the same size of A through D, but we also then tested with significantly larger environments that are E through G. So in this case, A through D are like 5 meters by 5 meters environment, but E through G are 25 meters by 25 meters environment. So it's significantly larger than the training environments we had. So here is some of the results. Yeah, here is some of the results. So this is for one particular environment, and you can see that our approach, that is the blue line, significantly outperforms the other approaches. And the vanilla LLP here is basically using critical regions, but just for sampling and not doing the hierarchical planning or task and motion planning kind of things. And when we do it with different robots, that is rectangular robot, the hinged robot, the non-holonomic car robot, and then the 8 degrees of freedom fetch manipulator, we see that in all of the settings, our approach is able to significantly outperform the existing approaches, and we get about 10x speed ups in the motion planning times. In the second best, the vanilla NLP did perform good, but you can see abstractions help a lot. You can see hierarchies help a lot. But this is again limited to deterministic motion planning problems. You cannot do stochastic, you cannot do proper task and motion planning with objects and everything. So what is the solution? So let's look at the stochasticity solution. So instead of creating a motion plan, we go back to policies and options again. As I said, we have options, we have initiation sets and termination sets. Those becomes our option endpoints, and you can go from one option to another option. I'm rushing through this because I want to go to more interesting work. What this also gives us is a way to automatically define a dense reward function. So let's say you have one option that is, and you have its initiation set and termination set. These are all automatically learned initiation and termination set. Nothing has been hand specified. What you can do is you can create, you use the previous approach to get a motion plan that goes from initiation set to the termination set. And that becomes a way to specify rewards automatically. So what we do is we give some good reward for each to reach the termination set. Uh, we give it some penalty to drift from these motion plan, and also we give it a dense progression reward to follow the motion plan. And everything of this is automatically generated. And now you can use deep reinforcement learning, and we use soft actor critic at the low level. And at the high level, you can do your search already. And you get your hierarchical planning and learning approach, which is using high level planning at the top. It is using deep reinforcement learning at the low level. So you can already be reactive and you can handle stochasticity very well. And you get your theoretical properties again of probabilistically completeness and download refinability that we had previously. We again tested it with some similar environments. We use again in navigation and manipulation settings with two robots. One of them is holonomic, the other one is not holonomic robot. And then we have a 8 degrees of freedom manipulator robot again. So here are some of the results. As expected, we will only have the paper if it outperforms the baselines. So here we not only outperform the baseline, but interesting thing here is this is the x-axis is the time, that how many seconds we spend on learning the entire policy, and the y-axis is how many what was the fraction of test problems we were able to solve. And we see we quickly solve all the problems compared to the baseline. And here are some of the more results. One of the interesting thing was that when we updated RRT replan, when we created the version of RRT to just replan when it fails, it performed significantly better than the soft actor critic algorithm in navigational settings when the horizon was very long. So each plan takes about 400, 500 steps to reach the goal here. But when the goal was a bit shorter, let's say 60 steps, that was the goal for the manipulation setting, soft actor critic outperformed RRT the plan by a lot. So what that says is that when the horizon is smaller, deep reinforcement learning performs better. And that is also the reason why we outperform both of them, because we are taking a very long problem. We are decomposing it into a sequence of small problems. Each option is now each option is very small compared to the overall problem. And that's why we are seeing significant performance in our approach as well. So why we are seeing better performance, as I mentioned, it's a smaller feedback cycle. We are doing RL over smaller horizon now, and also we are generating this automatically dense reward function. How are the solution quality? So here the x-axis is different environments that we tested on, and the y-axis is the average number of steps that we took in order to reach the goal. And you can see our solutions are much shorter than solutions from RRTD plan or soft actor critic itself. So we are getting more optimal plans. And not only that, the pie charts, or the pies over the pie over the uh, bars are basically showing, let's say if we have a solution computed from the algorithm and we execute it multiple times, how many times is it actually solving the goal? The darker the pie, that means we are solving the goal multiple times, more times when we are rolling out just the policy itself. So we want darker pies, and you can see the solutions are more reliable. They are solving more goals than not solving that. So again, the reason is smaller feedback cycle and dense reward function. So here is the overall approach. You get the input that has the occupancy matrix. You predict the critical region. You build these Voronoi diagrams that gives you state and actions, and then you do hierarchical planning or hierarchical motion planning with it. Great, but again, we run into limitations. These are all motion planning problems, either stochastic or deterministic, but still motion planning problems. It's basically restricted to going from one location to another location, or from going from one configuration to another configuration. It cannot do anything beyond that. What if we want to do something like, let's say, pick up an item, or the example that I give, get me a coffee from the kitchen, something like that? It cannot do it. And why it cannot do it? Let's look at like a simple example of the manipulation setting. What it has to do is the robot has to go from its current initial location over here to grasp this particular object over here. And if I plot a trajectory of the robot in this case, it would look something like this. Let's say we have another instance of the same problem, but with a different initial and goal locations. It would look something like this. And if we see on how the both paths would look in the space, there is nothing common between them. Even we know the problem is very similar to each other, but there is nothing common between them. And that's why we can't use the notion of critical regions here, because you won't find anything helpful here. However, there's a catch. If you convert these trajectories into the relative space of the object itself, now you see some relevance. So now we are assuming that the object is at always at 0, 0, and then you plot your trajectories accordingly. You see something like this. So if your, let's say, your object is here, you see your gripper moving from this to here and here. That's basically very similar trajectory that is being generated. Okay, sorry, something is wrong with my presentation. I don't know why it's not working. Mm. Okay, I'm sorry. It's not letting me switch slides for some reason. Sorry, I'm reopening my presentation and continuing from where we were. Okay, can everyone see my presentation?
Just a second. Still not seeing your screen.
I don't know. I'm sorry. I don't know what's happening.
Yeah,
Now?
you can see it.
Sorry for the hiccup. Okay. So once we convert these trajectories into the relative state space of the objects, what we see is there is a commonality and there is a critical region. But now because it's in the relative state space, we call it a relational critical region. And relational critical region gives us a symbolic vocabulary. So each relational critical region between two objects becomes a predicate that we needed for task and motion planning. And going in and out of these relational critical regions becomes our actions that we needed for task and motion planning. So here's how at high level it will look like. You have a bunch of training samples. I don't know. Yeah, you have a bunch of training samples. I'm sorry, I don't know why it doesn't want to let me share the screen. Okay, let's try this way. Okay. Is my screen still visible?
Yes.
Perfect. Okay, I don't know what's happening. Yes. So you start with a bunch of training data that are just the trajectories in the environment. You convert them into relational trajectories, and then you identify these relational critical regions. So in this case here, doesn't matter where the object is on the table. Whenever you want to grasp it, you need to come near it, and that gives you this area around the object where you can grasp it from, and that's a relational critical region. What we do is now we have from there you can invent a relation that is, let's say in this case, holding gripper, and also an invent an action that goes into this relation and goes out from them. So you get pick and place actions. Once we have these actions and these symbolic predicates, you can do task and motion planning over it. So we tried this in bunch of settings and we evaluated for different parameters. In this case, we want to see how generalizable these things are, how robust these things are, and how succinct and interpretable these things are. So let's, for an example, we do it for 5 domains, where in one domain where the robot has to deliver things in the cafe, we want to set up a dinner table, we want to do the structure building that we showed previously, and we want to pack object boxes with objects very tightly. So here is an example. So on the left, here are the training, what was the training data looked like. And because this is state based, we can collect a lot of data in simulator, and then we can transfer it to real world. So what robot here is doing is just picking up object from one location and placing it to some other location. And the training was done with a single object, as you can see in the environment. And now we have the robot in the real world that can pick up multiple objects and set up a dinner table for you right out of the box, zero shot. So we didn't collect any training data on the actual test environment itself, and we only did it in the training environments that on the left, that are on the left. Similarly, slightly less interesting, but this is in the sim, so we can see how much we can scale. So we try with single objects, again training with just a single object, and then we evaluate our problem with multiple objects. For example, on the right, you can see how many objects are there. You can place different objects on a single table, and from you can pick up from different tables as well. uh, in the other setting where we are building structures with the Kiva planks, the training data comes from again simulator where we are just manipulating at max 3 objects. So you can see that there are very simple settings where you have only at max 3 objects and you are picking and placing these 3 objects in different ways. And then once you have that, you can build significantly complex structures with these objects. So for example, here we are using at nearly 24 objects in test setting compared to only 3 objects in the training setting. We did it with the real robot as well. So we have data coming from the simulator, and then we are building these structures with the real robot. So here the robot is the everything that we need for task and motion planning is what relations are there in the environment, what actions can the robot take, and how to go from the high level to the low level. Everything is learned now. When we previously saw this video a few minutes back with the bimanual Yumi robot, everything was provided by the human, and now everything is learned automatically from the data. Right. And this is the last example where the training data is basically putting one object in the box in different ways. And then the test eggs to fit all 4 of them very tightly with each other. And you can see the algorithm. It's a very hard problem, actually. For humans, it's very easy, but for an algorithm, it cannot do it unless it learns these relations pretty nicely. And you can see that after a lot of retries, it finally figures out how to put all 4 in the box, and you cannot put anything else. And there are very few ways you can actually fit all these in the box itself. Right. So here are some of the learned relations that we are learning. So each red point is basically a sample from the relation where the relation is true. And you can see already that it is learning that, okay, to operate on the table, the robot has to be near the table, or to grasp something, the robot has to have its hand near the can, or to put something, the robot has to put something on the table, the robot has to put it somewhere here in the center so it doesn't drop or anything. Similarly, we are learning it for different actions. If you want to put a plank parallel to another plank, it has to be roughly somewhere on one of those red dots. Similarly, on the plank, something like that. Right. So here are some quantitative results that we can talk about. So here what we are measuring is something called generalization factor. We are seeing how many what were the number of test objects versus what was the max number of training objects. Behavior cloning, which is right now very famous, gives you a generalization factor of 1 because it only works in the settings where it has already seen the demonstration. So the number of test object is exactly similar to the number of training objects. But compared to that, our approach goes well beyond. So we can reach up to the generalization factor of 18. And also here, the limitation was the task planner because the task planner couldn't plan for more than 20 objects. If we had better task planners, we could have gone even longer, and we don't really care how many objects are in the environment. And when we talk about the robustness, that how much data affects our learning, we can see that with 100% of the collected data, which is not actually much, at max we had 200 trajectories or 200 demonstrations, that to just 50% of them were useful and was succeeding demonstrations, and 50% of them was completely useless demonstrations. We get the same performance as the state of the art task and motion planner with hand coded abstractions, but with even with lesser data over here, just 50% of the data, we are getting very good performance. So we also compared this approach with Codes policies. Codes policies won the ICRA Best Paper Award in 2023. What it does is it requires human to give all these Python APIs for robot. So let's say I need to write, okay, if robot wants to pick something, how can it pick something? If robot wants to place something, how can it place something? And then it takes these APIs to a VLM, and given a new problem, it kind of comes together with the code that uses these APIs in order to achieve that task. And you can see that while it does okay in some small problems, but when the problem size increases, it performs really poorly and it cannot solve any problem. So the Codes policies can only solve at max like 30% problems, compared to what we can solve, because CODIS policies cannot work with a lot of objects, which we can generalize to. Right. So if you want to take one thing away from this work, is that this was the first work which just takes raw, unsegmented or unannotated training demonstrations, learns symbolic models out of these symbolic world representation, symbolic models, what you want to call it, and then it can use it with task and motion planning to solve significantly complex problems. Zero shot. We don't need any additional training for new test problems. But everyone asks me, okay, now we are in the time of foundation models. We have ChatGPT, we have Gemini, we have Pi 0.5. What roles these foundation models play in these kind of work? So this is our ongoing work where we are using foundation models to learn these symbols for the planning itself. And we are using foundation models in three ways. One, we are using it to actively collect data. So a foundation model is helping the robot to determine what actions to execute in the environment just in order to collect the data. Once you have the data, and let's say some initially learned model, it can be completely blank. You would run into a situation where the robot thinks I can take this action in this environment because it fulfills the precondition, but you can actually not take that action. And from there, we invoke the foundation model's capability to generate new predicates, that is the predicate invention. And then we use foundation model also to evaluate whether these predicates are true or not. So here is an example. So in both cases, these are two different states. In both states, we are executing the same action, that is stack. In one case, when there is nothing on the plate, the robot is able to successfully stack the bowl and the plate. But when there is something already on the plate, the robot is not able to execute the stack action properly. But robot doesn't know that it because the current state is same, that the robot is holding the bowl and the gripper is not empty. It doesn't know that for something to stack on the plate, the plate also has to be empty. So we take these both images to the foundation model, and we ask it to generate a predicate that differentiates these two states. And in this case, the LLM comes up with is occupied plate predicate itself. And the interpretation of that predicate is no object is visibly resting in contact with the upper surface of the specified plate. So the LLM is coming up with this predicate and the interpretation. So next time when we want to evaluate this predicate, we can just take this interpretation that LLM came up with and the image to the VLM again and ask it to say whether this predicate is true or not. So we tried it in different settings. So in this setting, here is an example where the agent has to make a burger. So it has to first cut the lettuce. It has to heat up the bun. It has to heat up the patty and then make the burger. And this is one of the actions that we were able to learn. And all these predicates, whether the gripper should be empty, whether there should be something on the chopping board, where there should be you should be holding something or not holding something, is coming from LLM directly, and we are not providing any other inputs to it. And then you can learn predicates like cut into pieces and things like that. So I'm not going to go into the details, details of the quantitative results, but the second environment is where we are trying to see how generalizable this learning is. So can we go from a different training setup to a different test setup? And here is an example. So uh, we have different training configurations when we are learning the operators and everything. But then when we test them, we have different settings. So we have now more objects in the scene in different configuration. So now the goal is to clean the plate and pour something into the cup. So here is the idea. So we start. Okay, we start with the robot holding something. So it quickly figured out that, okay, I need to place the bowl somewhere. Otherwise, I cannot do anything. So it first placed the bowl somewhere. Then it picked up the sponge, and then it used that sponge to wipe the plate, and then it picked up the teapot and poured the, in this case, some beans into the teapot pot, and then it remembered that, okay, I had bowl in my hand previously, so I just need to go and pick the bowl up again to be in the same state. And that's how, and all of these operators, all of these predicates, everything that is needed to plan this entire sequence was learned from the data using the foundation models. So that is the conclusion. I would like to conclude here the talk that, okay, the idea that we can plan, the humans can plan, makes us intelligent, and our robot should be able to plan automatically as well. And a lot of my work has focused on how to learn components that allows you to plan. And I think we're doing good on time. We have some time for questions.
I have two more. Okay. Hi, sir.
Hello.
I have two more questions.
No, sir.
Okay. I have two more questions. How long did it take you to do the motion planning piece of your project?
I mean, are you asking about the motion planning work, or just how much time does it take to compute the motion plans?
To do what you're doing today with the choices and your overall motion of the robot.
I'm sorry, the question is slightly not clear to me.
Like just a general order of magnitude, a couple of years to do the motion planning?
I see. Yeah, roughly a couple of years, because but just to note that one of those years was a pandemic year. So give or take a couple of years, yeah.
Okay, and the other question I have is, since you're using generic robots, can you import libraries of other, I don't know if they're open source versions of how do you load a dishwasher or something like that? Is there an option to have library functions that you could include with your system?
Very good question, and the answer is yes. So the idea is you can use any off-the-shelf skill that you can learn. So let's say you learn a skill to do something, we can incorporate it in the system, and you should be able to use it with the system, because the capability of the robot should keep on growing. So the answer is yes. Any advancement that is being made in the adjacent fields of, let's say, skill learning or skill acquisition or policy learning would directly benefit here, and we can just improve the capability of the robot itself.
Oh, I have one more. I'm sorry.
No,
are you looking at Llama or one of the SLMs for your robot so that you get some more capabilities?
So we are right now looking into different other ways of doing, like behavior cloning and reinforcement learning, to increase the capabilities. What we have learned is behavior cloning is a bit clunky, and all these VLMs that are coming, that are a bit slow. As I mentioned, the VLMs cannot operate more than a few hertz a second, and some of them are even like 0.25 hertz right now, which are very slow. So what you see is the robot moves, then stays there for 4 seconds, then moves again, then stays there for 4 seconds, and then move, because it's running some controller at 0.25 hertz, which is very slow. So we want the robotics requires way faster output, and because all these models have, let's say, 30 billion parameters or 32 billion parameters or something, the inference takes a very long time. So what we are looking in is how to use RL more efficiently for the low-level manipulation or the low-level motion generation, and then you can have the foundation models or these VLMs doing a bit more like high-level planning kind of things, where it can be slow. It's fine, because you are doing it once in 15 seconds, it's fine. But the low level motion, which is being done 100 times a second, that has to be fast. So it's going to be a combination of VLMs with RL, in my opinion.
Thank you.
So, hey Naman, I'm Ritvik. I do have two questions. One on the line of learning capacities that you have built in your previous work before you started using foundational models, and the other one on actually using foundational models. So when you're trying to, so I'll go with the first one. When you're trying to build these learning or symbolic reasoning is what you call them. Well, when you have situations where your goal state itself is not very well defined, how do you operationalize in terms of creating plans for achieving that or
Mhm.
suboptimal goal state?
So can you give an example? What so there are multiple ways in which the goal state can be ill-defined. So one way
Yeah.
is
So
I
an
ask
example
you.
I can give you is like, for example, the shelf opening robot that you show for Boston Dynamics when you're trying
Uh-huh.
to open a shelf. So smooth motion is you just pull the shelf and it actually opens out, and you know the exact amount of force because it's previously calculated and so on. But in real world situations, we do see that the shelf might get stuck when you're trying to pull in the very first pull, and you don't even know the actual depth perception of the shelves, especially when you're trying to have very minimal uh, sensors to begin with. We just have a camera and so on. But humans, we are used to the knowing how deep the shells are, how much force we need to pull with, and in environments like that, where you actually are not particularly sure, a small anomaly occurs, how do you handle creating
Yes,
these?
excellent question. Excellent question. So, and that's why where I see a lot of future RL to be employed, that you can nowadays the simulators are getting better and better. So you have simulator like Mujoko and Isaac, which are basically physics simulator. You can actually randomize the parameters of physics, friction, force, how much force you are required, how what's the stiffness of the drawer and everything. And there are already works that look into randomizing all these parameters while training, so your policy is actually reactive already. So you are not just blindly pulling it with some fixed motion, but you are actually observing that how the state is changing when you are pulling this. So it's implicitly doing like a POM-DP formulation of the problem, that there is a latent friction variable. You don't know it, so you need to infer it from your observations. So that's why randomizing those parameters while training becomes helpful there. So does this answer? I mean, it's more
Yeah,
simple thing with physics
it's
simulation, yeah. And that's why
but
I kind of like reinforcement learning over behavior cloning, because behavior cloning cannot do that. Behavior cloning is just learning from one particular trajectory or few trajectories exactly how it did it, and that's why we need force stock sensors. We need reinforcement learning. I'm not saying that you need to have exact force stock sensors in your gripper or robot itself. You can infer that information from how joints are moving with how much force you are applying. So robots already have kind of implicit force stock sensors, and some idea of it. It can be very noisy, but I think that's sufficient at this point.
yeah. So the line of thought that I was thinking of was maybe using a subgraph of a knowledge graph representation as
Mm-hmm.
one of the states in the POM-DP setup, and then the unseen or unknown parameters to be this. But yeah, what you said, the approach is actually pretty good. I'll probably read through that. The second question is about the the utilization of foundational models
Right.
in these environments. I did perform a couple of experiments myself when I'm trying to generate plans, when I'm trying to generate schematic outcomes. And I did see even the best model with the best prompts that I could find is still not performative enough, or there's no explanations for those or certainty in what the outcome of these foundation models giving out. So I just wanted to hear from you. What do you see as a unique perspective that foundation models can add to already existing?
Right. So that's why we are not using foundation models to plan itself. And that's why we are learning these operators using foundation models, but not using foundation models to directly plan, because foundation models at long horizon planning is pretty bad. They do not understand it. They cannot keep track of the constraints that they need to make sure that follows. But at the same time, we should also agree that foundation models are very good at things that human would do in less than, let's say, 1 second. So let's say if I give it an image and if I ask, is there a computer in it? Yes, it will identify it because they have been trained on that data. They have been trained to do all those things. So foundation models has great situational understanding, but not great spatial understanding, or not great temporal understanding of things. So we are using that's when we are using it modularly in different modules, not just one end to end. And I feel that is going to be case going forward as well, because nowadays with all the agentic things coming up where foundation model itself can use different tools to do various things rather than it needs needing it to learn an entire thing. So now let's say a foundation model can use the Python interpreter to write some code and then evaluate it rather than trying to learn to evaluate it line by line. So if I write, like, let's say a equals to b plus c, foundation model doesn't need to learn what b plus c mean. It can just go to Python interpreter, run the code, and see what the output is. So now with these modular approaches coming, I think foundation models are good at modules, while while in a setting where you can keep check on them. So in our setting, we do keep a check on it. So for example, when it comes up with a predicate, we go and see whether that predicate actually uh, changes the applicability of action or not. So let's say when we add that predicate to our state, is it actually the case where we get one state where the action should be applicable and the other case where the action shouldn't be applicable, or are we still getting the same situation where the state are same and still action is applicable in one and action is applicable and not applicable in other? So we just disregard the output of the foundation model. So
So
there
like a
are,
verifiability test for the actual new state that has been added by foundational is
sorry.
what. So you're kind of trying to perform like a verifiability test of the
Yes.
entire simulation setting. Okay.
Yes, exactly. So all these verifiability has to be there, and that you can only do if you have like an access to simulator or access to verify the output of the foundation model. So I think that is needed right now. I agree that the foundation models outputs are very noisy, and even the best models are not that great.
Got it. This is a very interesting line of work that I find. I'll possibly connect with you offline.
Yeah, sure. Would be very happy to stay in touch. Yes.
Thank you.
Okay, thank you very much, Naman. This was very nice work and very nice presentation. Other
Thank you,
than the
Professor Shah.
little hitchup you had, but yeah, this is good. Good. Let's keep in touch.
Yes,
Um,
Professor. Thank you
I'll
so
be
much for
sending
inviting,
more.
and it was great. And sorry for all the hiccups that went in between with
Yeah,
sharing and
yeah,
everything.
it happens to all of us. Okay, bye
Take care.
bye.
Bye.
Can you once you can download it, put it up there, and once the source.